Okay, so we're talking about PyTensor. What is PyTensor? It's a library to define, manipulate, and compile computational graphs. So we're going to go through what this means in by examples. This definition was criticized by Bob Carpenter, one of the authors of Stan, on our forum. He was saying, like, back in the day, I was looking at Theano and I don't know what the hell any of this means, so we never ended up using Theano. And like, yeah, fair enough. So I think the best way to do this is to go through some examples of what does this mean and why would you want to use it. So what we're doing, I guess, in any program is we're building a computational graph that can sort of be understood as a collection of operations and inputs. So to look at like a really dirt simple example, here's like an addition, right? So you have like x plus y equals z, and you could think of this in terms of input nodes and operations, again, that act on those inputs. So I have two input nodes, x and y. I have an operator plus, and then I have an output z. That's the result of that operation. So these can be arbitrarily complex. Critically, in PyTensor, we're going to focus specifically on the directed acyclic type. So a lot of this should sort of rhyme with the types of causal graphs we're used to dealing with in PyMC land. Just now, instead of thinking about causes and effects, we're thinking about kind of the flow of computation. And we can introduce loops and things. We have control flow operators, but that's sort of down the line. And there's special logic that needs to be done to make that happen and sort of shove it into this directed acyclic framework. Okay, so that's kind of the graph part. And so how does this definition part work? And this is kind of, I think, where people get tripped up when they first see PyTensor. It's certainly where I got tripped up when I first saw PyTensor, is that you're building a function piece by piece in just lines of Python. You're not writing function decorators, although sometimes it feels like you should be doing that because everything is designed to look like NumPy. So that can be an advantage, and it can also kind of trick you a little bit coming in for the first time. So very simple example. In NumPy, you have some function like np.log, and you want to do some computation. So you have to declare some actual data. I make an array X, I fill it with some numbers, and I pass it into log. And what I get back is an actual array of numerical values. It actually executes this computation. So the critical difference in PyTensor is that, number one, the first thing we're going to pass in, this X is not a number, it's just a symbolic placeholder. So in my mind, PyTensor is really straddling this line between a symbolic algebra package like SymPy or Maple and a tensor library like NumPy. So like SymPy, we're going to be working entirely in symbolics. And so we have to start with symbolics, we have to end with symbolics. Unlike SymPy, we're not focusing on algebra per se, right? You can't solve quadratic equations with PyTensor. But also, unlike SymPy, you can do things like broadcasting. You can do things like linear algebra. You can implement arbitrary operations on these symbolic inputs, as long as you can write down kind of the rules on how to deal with them. So I declare a symbolic input, and then I have pt.log, which is going, so we're going to just switch the np to a pt, and then I get something out. What I get out is not a number, but it's a log.0. So what this is saying is that it's the result, it's the 0th output of an operator that's called log. And then what's the type of this? It's a tensor variable type, which is sort of our lowest level primitive. Well, one of our lowest level primitives for symbolic things. Okay, and then the most important tool when you're working with PyTensor is this method and function dprint, which stands for debug print. And what that's going to do is it's going to print out the graph of what you're working with what you've asked for. So how do you read this? They take some getting used to, admittedly, but the output's on top, and then we're going to kind of read down and inwards. So we start with a 1, and it's a scalar 1. So we're going to take that scalar 1 and expand its dimensions, so like blow it up so that it matches with this input vector. And then we're going to add them together, and then we're going to log them. So if you've ever looked at like a PyMC model and done model.debug, you'll get out like a really ugly one of these because you're looking at the log p function of your PyMC model, and you probably are just like, forget it, I'm not looking at this thing. But this is how it works. There's some intricacies. It'll truncate things when they get duplicated and repeated, and we'll see some of that later. But at the very basic, yeah, you go inside to outside, bottom to top. You can also get visualizations like with GraphViz, and I'll show you a few of those today. They're kind of a trap. I like them. Ricardo hates them. The problem is that they don't scale very well. So, I mean, just to cut to the chase, so there's this function py.print. You have to wrap it in an SVG because it was written quite a long time ago, but you get a nice picture like this. It's a little bit easier to understand. So this is the same information that we just saw in the dprint, but sort of colored and laid out for you. You have two inputs, a scalar 1 and a vector of shape 3. The scalar gets blown up, added to the vector, logged, and then you have an output. Yeah, and I mean, it could get some CSS love. It could also get some like TensorBoard interactive love if we had something like, PRs are open. Expand dims is an operation that adds dimensions to an object. So the scalar 1 is a scalar, but we want to add it to a vector. So we first have to inflate its dimensions once. Yeah, same as NP expand dims. So it'll make like a shape 1. So you see what comes out as a vector of shape 1. And then in PyTensor, the rules are that shape of 1 is special because it can broadcast. No other size can broadcast. I guess this is just NumPy broadcasting rules. But if you don't know them, 1 is very sort of special. So right, so what's technically going on is we have a bipartite directed acyclic graph, and it's composed of variables, applies, and then variables. So this picture down here, this is up backwards, like the arrows in my mind should flow the other way. But we're starting on top. You have X and Y as inputs to this apply. And an apply is just like a big box that knows how to do stuff. Like it's a wrapper. It knows that I get an X and Y, and I'm going to return a Z. And then attached to this apply is an op. But an apply is not an op. Yeah, so an apply has an op, but it isn't an op. The apply is more like the plumbing that connects everything together. So in this case, the operation attached to this apply is an add. So we're taking an X and Y, we're going to add them, and we're going to get back a Z. And then in this example, everybody's a matrix. So there's some like element-wise action happening here. So the apply would know, I should expect matrices, I should return matrices, I know how to propagate the shapes, I know how to propagate the D types. That's attached to this plus. So you can dig into these tensor variables and you can look at all of this stuff. So Y, if you recall, is a tensor variable, and if you ask for its owner, you're asking for the apply, this box that created it. So if you look at the type of y.owner, you get back an apply. So if you were looking for the plus, if you wanted to know like, well, what was the actual operation that created this? You're not looking for the owner, you're looking for the owner.op. So the owner, again, is the apply. The apply knows the operation that it's going to be doing. And so in this case, we have an element-wise operation. So an element-wise is just like a generalization of a scalar operation to higher dimensional objects. In this case, the scalar operation is a log. And so it knows, okay, you're going to give me something that's not a scalar, but I'm just going to do log to everything that's inside of that. If you wanted to, like, for example, implement a new operation like the owner is the parent in the graph, but not a parent in a simple DAG with just variables. So again, you have So the graph is bipartite, and you're never going to have a variable owned by another variable. You're always going to like interleave variables, variable, because variables are sort of like nouns and ops are like verbs. And so there's a syntax that has to be followed. You can climb all the way back up though. So if you look at the owner outputs, now you get a log 0. That actually is y. So like y.owner.outputs, you get y back again. And you could even, sorry, the inputs, that's the add node. And what I wanted to jump to was here. So the story can begin again. You can ask for the inputs to the owner, and now you're stepping up one more time, and you're getting like the next variables up the graph. So you've sort of like stepped through the operation, and now we're at the next level of variables. And again, it's always bipartite. So yeah. In this case, we've hit a root, which kind of have special meaning because you had created it yourself. Since we're sort of PyMC users first, you won't be used to ever creating variables because most of the graphs in PyMC that you make are inputless. You have like a random variable, and the random variable sort of knows how to draw from itself. Or if you compile a draw function, for example, you use like pm.compile and you put a normal in there, then actually there's no inputs because it just has like a random generator inside and it knows how to spit out values. But if you're working in a more general framework, you're going to have to create these initial root variables to sort of kick everything off. So when I say a root, that's kind of what I mean. Okay, so manipulation of graphs is kind of the big deal here. So far, like this is all a lot of machinery, and you might be asking yourself, like, well, why would I subject myself to any of this? And you would be asking yourself a very nice question. You'd probably still be asking yourself a very nice question after I pitch this part of it. But this is like why it's nice and why specifically it's nice in the Bayesian workflow. But why we've sort of clung on to this piece of software even after it was sort of abandoned by its original developers. And so the three things we can do with a graph is we can mutate it in different ways, interesting ways. So I sort of grouped these arbitrarily into three operations. We can do replacements, we can do rewrites, and we can do transformations. When I say replacement, I sort of mean like a one-to-one. We can lift out one thing and put in another thing. When I say a rewrite, I mean we can reason about the graph and change it to have a form that's more to our liking. And when I say a transformation, I mean a map from an entire graph to an entire other graph that has nothing to do with the original one. So these are quite nice. So we can start with just graph replacement. So the simplest example is I just want to reach in and pick a node, either a variable or an operation, or like an entire subgraph, and I just want to swap it out for something else. So let's say we have a graph like this. I'm going to, again, reading from the bottom, start with b and 2pi. I'm going to multiply them together. I'm going to take the sign of that. And then I'm going to add 1. Yeah, so this is the graph I'm working with. And let's say that instead of taking a sine, I wanted to take a cosine. I could just say graph replace. D is the graph. And then my target that I want to replace is C, because that's what I called the cosine operation. And I want to replace it with the cosine of B. And you get back exactly the same graph, except now this sine has become a cosine. So you're kind of able to go in and do surgery on these things. One other note that I kind of elided, but I want to highlight here, is that D, this output, is kind of living a double life. So on one hand, D is a tensor variable because it's the output of an operation. It's the output of this addition operation. But at the same time, it's also an entire graph. So it represents all of the computation that led up to the creation of D. So when I say like I want to act on a graph, I'm always going to act on the final variable that comes out of the chain of computation that I'm interested in operating on. And so I'll sort of interchangeably, can you toggle back to the original graph definition after finishing? Yeah, so this doesn't go anywhere. So we never have destructive operations. Well, we have destructive operations, but they're not in place in the sense that D didn't go anywhere. I just created this guy Z2. I don't know. I think maybe he was called Z at one point when I was editing this. I apologize. So Z2 is this graph, but then D is still the original sine graph. You could keep both if you're interested in having both. Could I go back to the previous slide? Good question. I don't. So yeah, we just have the difference is the sign. I don't know if I'm doing what you're asking me to do. If we had multiple likelihood terms, you would just add things together in the graph, but you can also act on graphs like jointly. There are certain, can you pass a list into graph replace, Ricardo? So yeah, you could have like likelihood 1, likelihood 2, likelihood 3, and I want to do the same replacement operation on all 3 of them. And that's allowed. You would just get back 3 new graphs that have all been mutated in the same way. Yeah, Will?
Yeah. I just wanted to see side by side, but I'm seeing now, so you're not really passing just like the function, you're passing the function plus the input B. So can you do like a graph replace with the opt of one of the applies then?
Ricardo, do you know this? This is like a bit of a sharp edge here. You have to target a subgraph.
I didn't get the question, Will.
So C is the outcome, in my mind, of sine of B. Yeah, you can do some surgery and you can say sine of C is now cosine of B. But could you do that without having to have B, the inputs, do that replacement?
You could replace, sure, you could replace C by cosine of E, a variable that you created yourself or comes from somewhere else. So it doesn't really matter what existed above. It kind of, the graph replace is just going to replace the variable by whatever you pass it. It just cannot be circular, right? You cannot say replace yourself by something that depends on yourself. That kind of you cannot.
Sure, but you'd have to have access to those variables.
Yeah, you have to have those things.
Yes. Something to do that.
Well, you just need the thing that you have in the replacement. So if Jesse goes to the next slide, then the only thing you need is you need to have that you went too much, Jesse, where you did the replacement sine by cosine.
Yep.
So you just need that value of the dictionary, right? There you define PT cosine B. You just need whatever you need to define the value of that dictionary. In that case, it was the B variable. You could, again, maybe you don't have the B variable, but you know what B represented. You could say, I want C to be PT cosine of B times whatever it was. It's confusing because there's 2 B's here, but you could recreate the graph from the beginning. That's also valid, if that answers. You just need to be able to define the thing on the values of this dictionary. That's a construct.
The next example might be like somewhat helpful in this regard, just to say that you can be extremely destructive and you can just like chop off graphs and replace things. Yeah, and maybe this is getting to what you're asking. Like say you have a random variable. So I have a normal, I want to take the exponent of the normal and I create this graph here. But then later on, I don't want this random variable anymore. I want to pass in something that I choose. So I'm going to define a new root variable that I just call x input, and I do a graph replace on my y, which could be like the output, the final observed variable of a PyMC model. And then I'm going to graph replace in this input variable. And so the new graph is just destroying everything to do with this normal RV, and it's just dumping in this input variable. And so now if I were to work with this one, I have full control over what goes into that X input. But also, like, I don't have to have access to like any of this junk that define the normal RV. Like, we're done with that. It just gets chopped. Okay, so a less trivial case is the case of vectorization. It's a little bit more complex than a one-to-one replacement. Sorry, I'm checking Aziz's message. You can replace the operators without specifying the edges. Yes. I think that's correct. Because I didn't need to know anything about like where X came from when I did this graph replace, right? I just know that somewhere in this graph, there's an X and I want it to be gone and I want it to become this X input. And this X input could be like an arbitrarily complex computation, as long as it doesn't depend on, like Ricardo said, you can't introduce circles, but this could be like some huge ugly function and I just want to swap in one thing for another thing, it'll just do it. Yeah, exactly. So the do operator is exactly an example of graph replace. And then also, yes, simplification. So if you have a complex function that's computing multiple things and you wanted to chop it off for some reason, and I just say like, I just only care about kind of like ending the computation here, or some input is like a complex function and you say like, I don't actually care about doing that big computation. I just want to know, I just want to put like the number 3 here and see what happens. This is kind of what this is useful for. This is the least powerful thing we're going to see. Yeah, that's why I started with it. Vectorization is a little bit nicer. It's also a one-to-one replacement, but it's a one-to-one replacement that kind of has to reason. Everybody has to reason together because it's going to change what the meaning of the graph is. So let's say I start with a scalar graph where I have, here I use dscalar to just say this is like a float64 scalar. I'm going to take the log of it. And now instead of doing if I try to just do a graph replace on this with a vector, I actually get an error because this graph is illogical. I was trying to add a scalar 1 to now a vector x and then produce a scalar y at the end. It doesn't make sense. So the tool we have to reason about this graph is the vectorized graph. And you do this, and then now it inserts this expand dims. Yes, it is a find replace. If there's X is used in multiple places, all of them get replaced. So you do vectorized graph, it's exactly the same, just X has become xvec, but now it's reasoned through the graph and said like, aha, in order to make this vector addition work, I have to expand the 1. And it'll do this for all of the operations in the graph that it knows how to work with. Okay, so that's kind of the first category of replacements. Then we have this category of rewrites. And this is really where PyTensor shines. We maintain inside of PyTensor this huge database of how to swap one representation to another representation that's somehow better. And so we have these different notions of betterness. But here's kind of an introductory example. We can go backwards from vectorization. So say I have yvec, which is the result of the vectorized graph, and I just want the 0th element of that. So this graph, you have the set subtensor 0. So I'm doing all of this computation on the inside, and then I'm just taking the 0th element of that. So it's quite wasteful. I'll compute the log of all of the x vector and then just throw it all away. But if you ask to rewrite this graph, and then look now, the subtensor gets pushed all the way inside. So PyTensor understands that actually the only thing you need to compute here is the 0th element of the x vector and then log and add that. So you've sort of gotten this savings for free. The database, where does the database live, Ricardo? It's sort of this ethereal object.
You mean the code? I'll put the GitHub link there. But there is, usually you import it and then you say, I want to register a new rewrite in this database. So if I show you the file, you're not going to see the interesting rewrites. You're just going to see where the database is defined. But I will show it anyway. Actually, the next
to like the rewrite stuff too, just to see like where the actual rewrites themselves are defined. So one type of rewrite that's common to run is stabilization. So this is a suite of rewrites that understand numerically superior way to represent something. And this comes up a ton in probability, doing computations with like logs with small numbers. So you have all of these like funny functions like log 1p, log 1m, right, that are better at maintaining numerical precision for really small numbers, but you kind of have to know about them. And the promise of rewrites is to take that away and just let you do the dumb thing that you expect to do, and then it'll just work. So in this case, I define a graph, a dummy input x. I do log of 1 plus x. We've seen this graph before. If I rewrite with stabilization, it's going to take this whole graph and just convert it to this graph here. So it's just going to do the log 1p operation on x. So it looked in and it said, aha, you're doing 1 plus x and then taking the log of it. That's a log 1p operation. I'm just going to swap it out. Okay, so I'll come back to some more rewrites, but in order to show them, I needed a better example. So I have to do like a little Quentin Tarantino thing here and switch topics, and then we'll go back. So the most powerful thing we have in PyTensor is the ability to take an entire graph and then transform it to an entirely different graph. So the canonical example of this is Autodiff. If you think about what is differentiation, we have a forward graph, a loss function that's defined in some way. And then what we want to do is take that graph, start at the very end, and then using the chain rule, kind of generate an entirely new graph. So we'll take the derivative of the final loss and then sort of node by node, walking backwards, accumulate up this new derivative graph. So in PyTensor, we have this function grad. It actually exists in just pt.grad. But if I take grad of our log 1p operation, you get this new graph, which is the gradient of the log of 1 plus x. It's quite big. There's this like cryptic thing called second, which I never knew what it means, but it just means we're going to broadcast two things together and then only keep the second one. So it's just a way to change the shape of an input. Okay, so we saw this gradient, but now that I have this big ugly gradient, I can tell you that there's another set of rewrites called canonicalize, which takes a graph that could be arbitrarily big and messy, and it converts it to kind of a standard form. So I'm going to call canonicalize on this gradient graph, and what I get back is something much, much nicer. I think you'll agree. So here was the original form when you just do the chain rule walking backwards. I call canonicalize, and you see what we get is just 1 plus x, and then 1 divided by 1 plus x. So it's just the derivative of the log of 1 plus x. So you can also compose things, yeah? So here I'm going to do canonicalize and specialize together. And now instead of doing division of 1 by 1 plus x, it introduces this function reciprocal that's going to somehow be more numerically stable than doing 1 over x. So this is kind of the point here. You have all of these different graph transforms, and you have these rewrites and these replacements, but you can keep chaining them together because all of these take as an input a graph and an output a new graph. And you can just keep mutating this graph over and over again to your heart's content until you're happy with the final result. So another example of a transformation that we work with every day is log p inference. So what PyMC knows how to do is to look at a generative kind of forward process and then say, okay, given this forward process, how do I then go backwards and work out the log p of data given parameters? So I'll spare you an example. You know how this works, but this is kind of the magic that's happening underneath. You're doing a graph-to-graph transform. Another example, hypothetically, would be doing integrals. Okay, we can't do that. We can't do everything. But in principle, that would be what it looks like. Does the database look for conjugate distribution simplifications? No, but it could. So PR is welcome. That's a drum I've been banging, but you know how time is. And I mentioned that everything is composable. Yeah, so we're going to go through a series of rewrites, and you might be surprised what we come up with. Starting with this log 1 plus x. You could say, okay, instead of doing log 1 plus x, I want to do log 1 plus the x of x, right? So I'm just going to do a graph rewrite and go in and replace x with the x of x. And then I get a new graph. It just sort of does that rewrite in place for me. And here you see I actually have x on the left and the right, and that's fine. Yeah, I've just added more operation around it, and it'll just happily do that replacement. And then we can rewrite it. And I don't know, did you know that that was a scalar soft plus? This is sort of this this idea that we've all been working in this probability space for a long time. We know a lot of the tricks, but you might not know them all, or you might not be thinking about them at any given time. So having PyTensor kind of hovering in the background, watching for stabilizations is quite nice. Okay, so this is all fine and dandy, but where is the computation? So the end of all of this, once you've done this graph surgery, once you've got something you're happy with, you're going to call pytensor.function. And that's going to convert a PyTensor graph into an actual callable Python object. In the default backend, it's going to compile C code, and it's going to dump it into a temp directory somewhere on your computer. You can also ask for a compiled JAX code, like JITted JAX. You can ask for a JITted Numba. And we're also actively developing the PyTorch backend, so you'll be able to write JITted PyTorch as well. And all this is possible because we have this sort of backend agnostic graph representation of the computation that you want to do. So as an example, I'm going to define a dummy input. We'll take the sine and the exponent, and then the cosine of the inner product, and this is what you get. And then you can call pytensor.function. The semantics are that the inputs come first, and it always must be a list, even if you have nothing. So if you were compiling a random draw of a normal that has no inputs, you would still have to put in empty brackets there. And then the outputs do not need to be a list, but they can be. If you want to have multiple outputs, great, make a list. If you have only one, just pass one. What you get is this compiled function type, which is like a little wrapper. On the inside, it has the actual computation that's going on, but then it also does some some input validation and some other helpful stuff for you. And you can use it like any other Python function. One thing about the rewrites, every time you call function, all of the rewrites can apply. So we showed you all of this stuff about like, oh, I'm going to do stabilize, I'm going to do canonicalize. At the end of the day, that's typically not going to be necessary. As a user, you'll just write a graph, you'll dump it into a function, and you'll call function, and then function will handle the stabilization for you. The only place I can think of where it's good to call the graph rewrite yourself is when you're working with gradients. If you have like a gradient calculation and then you want to use that gradient in a computation before you compile, it's nice to canonicalize and simplify the gradients in order to have something a little bit easier to work with. There's actually a PyMC function called rewrite pregrad. So PyMC does that under the hood every time you ask for MCMC. So you can check out these slides. I mean, I feel like I'm belaboring points, so I'm just going to skip through this a little bit. We do things, we do memory optimizations, so we actually in-place operations to save memory. We do a lot of like loop fusion and combining operations to save passes over, like looping over arrays to do computations. So it's really doing a lot of optimization for you. Here's an example of compiling to Numba. Yeah, so you just pass mode equals Numba, and then now I get back this graph, which will actually have different rewrites applied. So when you have a specialized backend that you want to rewrite to, you can define specialized rewrites to say do something in a certain way. Okay, and the Numba function works fine. So just to wrap everything together, I'll quickly show what logistic regression with gradient descent looks like. You all know these equations, so I'll skip it. So we have to define symbolic inputs. I have a placeholder for the data and the targets, and then a placeholder for each of the parameter vectors. So I'll have a bias term split off separately from the coefficients. I define sort of this probability, like squeezed by a sigmoid, and then define the cross entropy loss. And I do this thing where you give the variables names, just so that when you do the deprint, you can see like where did the class go, where did the cross entropy go. Okay, and just to show, kind of like belabor this point about why these graphs aren't great. So here's what the loss function looks like. It's actually not that bad, like if you stop and look at it, but I would argue that this representation here is a lot more compact if you're used to reading it. So just to say, this is why when I show these things in presentations, Ricardo always cringes, because just look at this, dude. Okay, and so then we need to compute updates. So we'll just do a really dumb gradient descent. So to get this, the gradients of the loss, I'm going to use grad. I do this canonicalization and stabilization on the loss. And then I take the gradients with respect to alpha and beta, and then compute alpha prime and beta prime just using this formula. So again, I'm sort of like stepping through and doing all of this. In like JAX or NumPy, you would be wrapping like little wrapper functions. You would say like, okay, here's the update step function, here's the compute the loss function. Here, I'm just symbolically working with everything, and then I'm going to hold off on what I actually want the inputs and the outputs of my functions to be until I'm done in the very end. Okay, so kind of like emphasizing this point. So okay, I compile my training function by calling PyTensor function. I'm going to pass in x and y, eta, the learning rate, and then the current values of alpha and beta, and I'm going to return the loss just to track it, and then the new values of alpha and beta after applying. But then I could say, oh, hold on, like I computed the probabilities, but I actually want to compute class labels, but that's not a problem. I can just define another new dummy variable, which will be a threshold probability, and then I'll define my actual class assignments as this, where the probabilities are greater than the threshold, and then I can compile a second function, again, like recycling inputs and outputs. So this time, instead of returning the loss, I'll return the probabilities and the class assignments. So it's quite flexible. You don't have to make any decisions about what the final form of your computation is going to look like. This is one of the advantages of working with this kind of object-based API. Then you can deprint the functions themselves and kind of see what PyTensor has done under the hood. And just to point out a few things, so here's my cross entropy. There's multiple returns here, so you can see that this is the first level, that's return 1. This is the first level of indentation. This is my alpha updated, and then there's this level of indentation. This is my beta updated. And no, there's nothing inherently probabilistic about PyTensor. It's all just agnostic computation. It's going to reuse things whenever it can. So you'll see that it compiles these, like reuses these like throwaway functions down here, these composites, and it's going to, anytime it sees like, oh, I'm doing, the negative of the division of these two things, it's just going to replace it with that function to save on computation. So it tries to be smart. And then, sure, we can train the thing, and it trains fine. Okay. So this is PyTensor in a nutshell. You have, you make these graphs out of operations and variables, and then you can mutate and play with these graphs, rewrite them and transform them, and then compile them into functions, potentially doing transpilation into other computational engines like Numba or JAX. So link to the documentation here. So how does this compare against other things? We're really putting like the front and center focus is these graph objects. So everything is lazy computation. It kind of has that like TensorFlow 1.0 design, but it doesn't suck like TensorFlow 1 sucked. You don't have all of this like with contexts before you're able to do any computation. It's all very functional, right? You're working with these objects, and every operation returns a graph, like takes a graph and returns a graph without any side effects. And it's a strong focus on hackability, right? So if you want to add a new operation, it's very easy to define a new operation. You might have seen that PyMC example notebook where it's showing you, well, how do I make a new likelihood op? And it's just a little bit of boilerplate code. But you can shove absolutely any Python computation that you want inside of the perform method of an operation. And then PyTensor will sort of wrap it up and know what to do with it. It won't know how to take its gradients necessarily, but you will be able to insert that into into an arbitrary graph that you want to work with. And it's completely ours, so it's like a reason why we like it. Of course, Nobody else in the entire world uses it, so that's sort of a negative as well. It has a long history. It started as Theano. There's been sort of a shift in tastes in the deep learning community. I think sort of started static, and then Torch came along and kind of nuked everybody because it was eager and everybody liked the eager thing, and everybody switched to the eager thing. And now people are coming back and saying like, well, wait a second, static is actually quite nice. So there are concepts inside of Theano that have stood the test of time. Others have aged a lot, and there's a lot of corners of the library that you feel that like this was written in 2011, because it was. Acera was kind of an intermediate form. It was updated and cleaned up the code base. It added the alternative backends, and it kind of proved that there's interest for a library like this. I still see talks where people reference Acera and talk about all of the neat things it can do. They never reference PyTensor though, because no one knows that it exists. Why are we using it? Basically Stockholm Syndrome. Okay, serious answer. The reason why we're using it is because when the decision was made to go all in on Theano as the backend for PyMC, it really highlighted that the things that Theano did were very, very powerful in the Bayesian workflow. And I've sort of alluded to this, but this idea that you're going to define one graph, and we're going to be really opinionated about what that one graph is, right? You're going to define the generative graph. And then from that generative graph, we will just be able to transform into anything that we require in the Bayesian workflow. We can transform it into a sampling function. We can transform it into a log probability function for inference. We can mutate it into graph rewrites for things like the do operator or the observe operator or the unobserved operator. None of those things are like obviously, it's not obvious how you would implement any of those things in other backends without a lot of like structure. But the sort of idea of a graph structure just gives it to you for free. These stabilization operations are also really powerful and very relevant, like I said, for Bayesian inference. So you can pass in logits P as logits, or you can pass in pm.math.inverse logits, and it's exactly the same. Then there's this whole other suite of rewrites that exist to help you out. You know, did you know about log1mexp? I didn't. But if you do this operation in a PyMC graph, you just automatically get it, and you never have to worry about it. Linear algebra is another place where this comes up, and like GPs. So a thing where like you have a Kronecker structured covariance. Like, did you know that you could invert both of those components of the Kronecker and then take the Kronecker in order to save on the ON3 invert operation? Like I didn't, but PyTensor does. So if you do a solve of a cron of x and y, it will push the solve inside and do solve x, solve y, and then cron the two things together. And we're trying to add as much of this stuff as we can so that as a user, you don't have to be a numerical computation expert in order to get good programs. And yeah, this lazy computation also makes it easier for us to interop with other things. If you want a Rust backend, you know, open a PR, please, and we'll have a Rust backend. So there's a catch though. It's hard to keep up with the times. There's very few devs looking at it all the time, so bugs get fixed sort of more slowly, and there's basically no resources. So whenever you have to interact with PyTorch, whenever you have to interact with PyTensor, you're probably going to have this feeling of like, what the hell is this, and why are you making me look at your dumb hobby project? Like, I just want to write a Bayesian model. Hopefully, this workshop will help get some more eyes on the project and make people feel like it's not this like ugly thing that I have to deal with sometimes, but I never want to. So yeah, that's kind of the high level, and we can talk questions, or we can just kick it straight over to Ricardo, who's got more content.
Yeah, let's just see if there's one or two questions. In the meantime, I'll start sharing.
Yep.
Okay, I guess that's a no. Thanks for the claps. Thanks, Jesse. for presenting what nobody knows. And now hopefully they will. So the idea now, second part would be just to break the fear a bit more of what PyTensor is. You got the big picture from the outside, and now I want to spend I will keep it shorter than I intended originally, but we'll spend maybe 20 minutes rewriting PyTensor from scratch, like the basic building blocks, ignoring PyTensor, but everything is going to look very much like PyTensor. And the idea is just to give you an idea exactly what do you need and what are the things that are going to be in the middle when you start working with PyTensor. So think of it like a Lego version of the library, but you'll be pleased to see that actually many of these things work, and they even trick PyTensor into thinking this is valid PyTensor code. So if you remember Jesse's slide, I will open it actually. PyTensor graph structures. Ooh, it's a read the builds. It will work. The picture is there since 2011, so I guess. Okay. We're going to build the building blocks that is in this picture, which are types, apply nodes and variables, and operators. Okay, and we're just going to use simple Python code. Obviously, PyTensor will always have some more complexity, but these, I think, gives you like 99% of the idea of what's going on. So I define in this notebook class type. This will be the base class for the types of our variables. So variables have a type. So tensor variable, it's a variable whose type is a tensor type. Okay, it kind of defines what type of variable it is. Like, is it an array variable? Is it a scalar variable? Is it a slice variable? Is it a dictionary variable? Is it a tuple variable? Most of the times you're going to work only with tensor variables, which are the array, kind of like NumPy array type of variables. But we'll implement it later. This is a base class. It doesn't say yet what kind of variables. Just base type, class op, and we just put a string just to show the name of the operator when we define it. And then the node, as we said, PyTensor is this bipartite graph, right? I can magnify. And it has two types of nodes. The variables, which you define here as a subclass of node, and applies, okay? Variables are going to take a name if you want to give them a name, and they're going to take a type. Okay? And I'm just saying self.name, self.type. They're going to have an owner, which is the apply node that creates them, unless they are root variables. Here, in this implementation, I decided that you cannot pass it to init. You have to manipulate it from the outside. I'm not sure in PyTensor which one it is, but this will work fine. And then I just added a nice rep, say, to create this variable, just define type equals blah, blah, blah. I guess you could have name. That doesn't really matter. Name is like just type hint, doesn't really change the behavior. And then an apply, also a node. It has an op. It has a list of inputs. Let me make this a list of variables. Now that they are variables, and outputs, which will be also a list of variables. Okay, I save those things and I do a check that the things you said are going to be the outputs of this node don't already have an owner. So they don't already have an owner, which means they don't belong to another apply node. This is a check that exists in PyTensor. So basically, you say when you create an apply node, you already create what are going to be the output variables. You don't actually ask the node to create the variables. You'll see these in the code. And one of the checks it does is to make sure, since you are saying this variable is an output of myself, I'm going to make sure that it's not an output of something else. And then a representation. Okay, so with these base classes now, we're going to try to create like a first concrete graph. First thing we need is a real type. So we'll go with tensor type, which just has a shape and a d-type attribute. In PyTensor, the tensor type shape can be a mix of tuple of float or none. Float means, int or none. Int means this is going to be a static shape, cannot change. So you saw Jesse saying, I want a tensor of shape 3. Or it can be none, meaning over multiple function evaluations, I'm allowed to change the shape of this. And you give a d-type Usually we default to float 64, but if you want to do like indexing operations, usually you have to say it's integer. If you want to run stuff on GPU, usually you want to work on float 32. So anyway, we have that flexibility here. I implemented a simple equality. It will be used later, but just this type is equal to another type if it's the same, and the shape and the D type change if it's the same Python type. Okay. Once we have tensor variables, we can create a first operator that works on tensor variables. Let's do an addition without broadcasting. So an addition that works if two inputs have the same shape and also the same type. So not worrying about what happens if you add a float 64 to an int 64, for instance. The op needs basically what it needs right now for us to define this symbolic graph that doesn't do anything yet is a make node operation. Okay, the make node creates this blue box that's going to say here is kind of piping, right, like Jesse said, from some inputs to some outputs under some operation. And apply means, if you want in English, is the application of an operation. Okay, so every node has this method. It's not I don't think op is implemented as an abstract class that raises if make node doesn't exist, but it fails. So what does make node need to do? Make node needs to return this blue box we saw in the graph. It needs to return an apply with an operator, usually itself, right? In this case, addition, and it has a list of the inputs and the output variable, which is, again, this kind of placeholder for the output of my computation. And it has to be able to define it specifically. So in this case, we have to find, okay, sorry, let me go back to the beginning. We check that A and B are both tensor types. Otherwise, we say this is not a valid type for this node. And we check they have the same type, which I implemented here, saying it has the same shape and D type. Then the output type, given these constraints and the fact I'm doing an addition, is going to be a tensor type. Shape, I just pick the shape of the type of A. Could have been B is the same. And the D type, I took it from A. Okay. Once I have this type, I can create a variable with that type, and that will be my output variable. And that's what I put in this list. Let me see if I missed something about. No, I think I'm missing something here about how the output owner gets changed. I guess. I guess it comes later, or I've broke that code. This code should be working. Apply node when it initializes. Sorry, okay. The node, when it initializes, it goes through the outputs and say, I'm going to be the owner of this variable. I was looking for this line here. I didn't see where I wrote it. After checking that no one else said, I'm already the owner of the variable. So when I return here this apply itself is going to say output owner is myself. Okay, we can look at those things here. So we created the addition operator, we created a tensor type, and now we can try to actually create the first PyTensor graph. So first thing we do is we're going to initialize the addition operator, which is just a class, make it an instance. And here is that beautiful line. And then I'm going to create a root variable for my graph. It's going to be two x and y. First, I have to create a type. It's going to be a double vector, so a float 64 vector. Here I decide I'm going to be a shape 10-1. So I define this type, and then I create two variables with that type. Okay, x and y. Here I'm on purpose doing this very laboriously and very, I guess, not nicely, so that you see all the kind of piping. And then in the next iteration, I'm going to show how we just add some methods to do some of this work for us. Anyway, I created x variable, y variable, and then I say add make node with these two inputs. And this is going to create this apply. And then I say, OK, I want to access the only output of this variable. So I do this like list unpacking to get something that I call x add y. Okay, I give it a name here. I call it x plus y, just so it's going to look nice later when I print it. And I check the thing I was a bit scary. How did that happen? What is the owner of x add y? And it's this apply node. Okay, so this is the first graph. We did two variables. We did an apply node that combines these two variables to make a new variable that we call x hat y. Before I go to the next one, I'll let just 1 second, like if there's any lingering, immediate burning question. Feel free to chat, I'll come back also.
Oh, quick question.
Yeah.
Where does the actual addition logic happen?
Nowhere yet, on purpose.
Okay.
The only thing that happened is there's an op called addition that's incomplete op. It doesn't yet have everything. That knows just how to create apply nodes with itself and knows how to reason about what's the output variables types, or knows how to create an output variable that's compatible with its given inputs. In this case, it's a very restrictive one, so it's easy to reason about. What if there are multiple owners? A variable can only have one owner. That's the rule. Like a variable is literally either something the user provides from the sky or the output of a computation. A computation can have multiple outputs, but all those are a variable of a single owner. All right, here is a second, second operation, sum. Sum is almost as boring, except it takes one input. And here I'm saying, okay, it has to be a tensor. And then what should be the output of a sum? Okay, it should be a tensor type scalar. So shape is a scalar, and the D type should be the same as the input. So I create this type, I create a variable with that type, and here I return and apply with myself, the sum operation, the input, and the new variable that will be the output. Okay, so here I initialize the sum class to be a sum operator, and I can play this game again with what I had before, the x hat y. I say sum, make a node, give me the outputs. There's only one, I retrieve it. I give it a name, and I confirm again that this is a thing that comes out of somewhere, and it comes out of this application of x plus y, and this is just the name I gave. It's one single variable, and outputs something I called sum of x plus y. Okay. And actually, at this point, after I do just some Python black magic to make PyTensor think that these variables are actually variables, PyTensor variables, I can call drint on these, and I get a graph representation of what we just created. X, Y, addition, and sum. I don't know if I can treat it into also saying what's the type of the intermediate variables. I can, okay. It's a tensor type scalar output, and the intermediate things have shape 10, and they are all float 64. Okay, now to the question of where is the addition, where is the sum? We need to add new methods that I on purpose didn't do. So the second part will be, now that we have this symbolic graph, how do we evaluate? And here it's, the first part looked 99% like real PyTensor code. This doesn't. This is like the simplest way that you could grab a PyTensor graph and try to evaluate it for some computation. There's one method missing in the node that I'm here monkey patching. Usually when you define, not in a node, in an op. Usually when you define an op, and this one is actually required to create a real PyTensor op, you need to define the perform method. Get something, return, doesn't return anything, you'll see that, okay, and does something. If this op was a PyTensor graph op class, it would require you to define it before you can initialize it. But we created dummy. We created everything from scratch, so there is no requirement. But here I'm kind of monkey patching it. I just wanted to clearly show you can build a whole graph without saying anything about PyTensor. How do you actually compute real stuff? So perform method is a method. So first argument itself, obviously, it's gonna take in this dummy case, just gonna take a list of inputs, and here we're gonna assume these inputs are already evaluated inputs. So they are real, like NumPy arrays you can do operations on. So we unpack them and we return a list with the output values, which is just a plus b. This here is supposed to be literally this. This should be valid code, okay? Just a plus b is a bit overloaded. That's why I'm being explicit here. And the sum method takes a, you compute the sum, you return it. Okay, so here then is the most dummy way of writing an eval kind of loop. we want to evaluate a variable, and we are given a dictionary that tells this variable has this numerical value. So let me start from the bottom. Let's say I want to evaluate the sum of x plus y, and x is going to have a value of a range 10, y is going to have a value of a range 10. Okay, we go in the loop. If it's already in the dictionary, the value of that is what's stored in the dictionary. Otherwise, if we got here and there is no owner, it means it's a root variable. You must have given me a value for me to be able to kickstart, bootstrap this computation. Arrays here, an error if that's not the case. Otherwise, it's a recursive, dumb recursive algorithm where I say, let's eval the inputs first. So I call itself eval input given for all the inputs in the node of this variable, the apply node of this variable. Once I have them, I'm going to call the perform method that I just monkey patched to get the eval outputs. I'm going to put them in the dictionary. I'm going to finally return the one that was requested by me in this step of the iteration. And here we see that here we were able to create our first evaluation and get a beautiful 90 as an output. One thing I want to show is that the way this was written, it also means that I could actually just say, actually, I already have the value of x plus y, and that happened to be a range 10. So if I give that, then I get 45. It means like I provided an intermediate result. I didn't need anything above, and the function works the same. Okay. The reason I highlight that is that PyTensor function works very much the same. When you say here, you can say, like you could have said, I want a function from x, y to our output, which was sum x add y. This does need to be a list. And this is going to expect 2 inputs, 2 arrays. Or I can say, actually, I want a function from, what was it, x add y. And then this compiles a function that expects a single input. And the eval here was to show exactly the same logic works. All right. Any questions about evaluation before we go to the beautiful world of constants? All right, constants. Constants need some special reasoning. And there's 2 ways we could have implemented constants, or the Tiano guys could have implemented. They could have implemented as the output of an operation without inputs. That's deterministic. Or they just said, okay, that's a bit silly. Let's just say constant is a special kind of variable that has data. And once you evaluate the constant, you can just retrieve the data from that variable. Okay. And this is the way I did here because it's the closest to PyTensor. Now eval has been extended to work with constants. Everything else works the same. And here I create a constant. It's a variable. It needs a type like our root variables need, but it has 1 extra argument, which is data that our variables didn't have. Here I create, I don't know, I call it 2. I guess I changed this at some point. This is not 2. This is 10 tenths, as you can see. Let's make them 2. Here is a constant of 10 twos. Okay, once you have that, you can, it's a variable, so everything, all the rules work the same. So you can say, make me a node where you add x and this constant 2, and give me the output, and I can evaluate it, and I get addition for inputs of the same type. I ran this out of order. Anyway, you'll believe me that this works, and you can add x to 2. Can I just run all? Run all. Yes. Okay. Wow, that was fast. Here it is. I was able to add 2 to everything. All right. So once we have constants, we have almost kind of everything we need to start doing real stuff. I'm just going to take a side step to just make these things easier because, you know, this add, make node, then give me the variable. It's a bit painful. So in PyTensor, one thing you can do with a type is to call it, right? If you know Python, it means there's a dunder call method that you can overload to say what happens when you have an instance. My type equals type something, and then what happens when I do this? Okay. In PyTensor, that's overloaded to create a variable of that type. perhaps intuitive. So now when we have a type, we can just, instead of saying variable type, we can just call it, and that's going to create a variable, optional with a name and the type. The other thing we overload is the call on an operator to call make node. And if it has a single output, to just kind of extract it so that, all the ones we had so far, we just get the variable back. We don't need to do that annoying list unpacking. And here I'm monkey patching call to the op class. I did the same for type. And I'm also going to monkey patch the eval routine we wrote to exist in every variable, and the dprint from PyTensor to exist in every variable. These also exist in PyTensor. And here, okay, and now we're going to see those in action in one last extension that we needed just to make the last example interesting. I'm recreating the sum operator, but now it's a parameterized operator, meaning once you initialize it, you can pass some information. Here you can say, what are the axes over which we are going to do the sum? Instead of assuming it's always going to be all the axes and output is always a scalar. So you define the axis here, and then the make node has to be changed to reflect this. We still have to check, is A a tensor type? If not, is a variable whose type is a tensor type? If not, raise. Otherwise, what's the output shape? And now we need to use that axis information. Is everything that was not summed? That's what this loop does. And then my output variable is a tensor type with that shape, and the D type is the same. And here I'm already using that helper to just create output variable directly by calling on the created type. Okay, then I can return it. And perform method is just changed to access self.axis. So here is a more interesting, or not more interesting, but example using this. Let's create a D matrix type. Let's say it's a 3x5, just so that we can see the axis working and float 64. X then is a variable with the D matrix type of 3x5 called X. And here I could have done just this step here. Let's say the name was X. This worked the same because we overloaded type again to make a variable. And output now is a bit more readable. It's just initializing the sum operator. In this case, we're saying it's axis 1, and then calling it. In this case, I'm doing a nested call and addition of X with X. And now we see the output type is just a tensor type float 64 of shapes 3, so a vector, because we reduced this second dimension. We can still treat PyTensor to dprinting, and we see here the parameterization shows up here. And you'll see these in the dprint, the operators that can be parameterized. Usually there'll be a name, and then there'll be like, how is this operator parameterized? You saw with the expand deems, it was saying what axes were being expanded. And we eval, and we got our second evaluation of the day, or the third if include constants, and we get a nice vector of length 3. Okay. And that's kind of, okay, that was the idea, was just hopefully give you a hint that this need not be extra complicated, and it really isn't for most things you're going to work with. And give you some confidence if you want in your free time to go and start looking at these perform methods. It actually exists, it's a bit different. Make node is almost the same, and understand this difference between variables, their types, operators, apply nodes, all that. Yeah. Will?
What does the inheritance with op get you? Either here or then also in the full package.
What do you mean the inheritance of?
So when you inherit and make mole, a new class mole, why inherit from op?
I mean, that's kind of what we decided to be the base class of all the operations.
Does it give you anything? Like, is it?
Yeah, so it gives, well, it gives, yeah, it gives you plenty. So it gives you the default call method that we monkey patched. All these methods we monkey patched. So where was the call? Making easier to work with. So it gives you the up call. It gives you some automatic hashing in some cases to say whether, and the equality to say whether an operator is equal to another. And it forces you to call perform. And other than that, I mean, it's just normal Python code. We are working with objects. We just make sure there's some hierarchy. So we just make sure all operators subclass another operator. But it's really, it shouldn't be a very complicated object, and it isn't. So you saw so much that we were able to trick PyTensor into believing that all the things we created were valid PyTensor things, right? Because indeed, it's always not doing much more. Yeah. Okay, so the last part I want to go is, once you have a graph, what would be the dumbest way that we would go about starting doing some of these interesting things that Jesse mentioned, which would be rewriting them. And for that, I just created a new operator, a mul operator. It's exactly the same as addition. We allowed it to broadcast here shapes for just to be a bit more fun, but this only works if the shapes don't have nuns in it. And this is how mul looks like. And so starting with our operator, our graph of summing the addition of two x's, we will try to do it first rewrite to think about, okay, adding x to itself is the same as multiplying x by 2. So let's see how we could rewrite that. We're not saying that's necessarily better or there's any advantage, just an example. For that, and here I'm going to do it like really the hacky way. So I'm going to kind of create the graph I want, and I'm going to mutate the original graph. I'm not even going to use anything as nice as a graph replace. I'm really going to work on the objects to just show how a rewrite can be done the dirtiest way. So I define a scalar variable, and I define the graph I want to replace the addition of x by, which will be a multiplication of x with a constant of 2. Okay, and here, and that's why I allow the multiplication to broadcast. This is just a scalar. And this is the magic. You know, it's dumb, but that's all you need. So the only thing we need is to, from the summation, go to the first input, which is addition, and just say, I don't want this out of 2x's. Actually, I want you just to be 2x. Okay? And now we deprint and we see that this graph is what we wanted. Okay? Literally, we just played with the fact that the apply node had a list of inputs, and that's a mutable object in Python, and we mutated that list. This is what PyTensor does under the hood. After being very careful to copy your graph first so that it doesn't mutate your original object, it literally mutates the list of inputs. Once you have that, you'll make yourself believe that everything works the same. We are able to evaluate this graph. We get the same numerical outputs we had before, but now we use the mul of x and 2 instead of x plus x. Okay, the proper way, it's not much more interesting. We just clone the graph first. So here I recreate the graph just to make sure, well, because I mutated the previous one. And I just do a step first where I clone the graph. And the cloning is basically kind of, if you saw the objects, you shouldn't be very surprised. What we do is recursively, we clone the inputs. Once we have the inputs cloned until now, we just create an output variable of the same type as the ones that we had there. And we say, okay, now I want to replace the application node by a new apply with the same operator, but the new cloned inputs and the new cloned outputs. I save that in the dictionary. I return the one the user requested, and we clone the graph. So literally, like, you pass something, you get something that behaves exactly the same, but it has the different variables that were created here and all the inputs. We can deprint, looks like the same, but new out is not out. And the first input is also not the first input. Okay, that's just proving that the clone works. I'm going to skip this part, but one of the things that, yeah, I'll skip this, okay? But we just did something so the rewrite works a bit more nicely. Like what we did here was, we kind of had to hack and say, If I want to change 2x, I have to see where it's used, find where it showed up in the list, and then replace it. This doesn't really scale well. And for instance, there could be multiple variables that used x plus x, and I would want to find all of them to be able to change the entry to 2x. So for the sake of time, I'm going to skip that. But if you want to go later in the notebook, there's some code that finds what variables, what apply nodes is this variable used in, so that I can go through that and replace them, all of them. And so believe me, that exists. And I'll show you just how a rewrite looks more like in PyTensor land. Okay. Usually we have these functions that just reason about the graph like very locally. They take as input an apply node, and they return as output either a list of variables that replace the outputs of this application node, or none if my rewrite doesn't apply here. So a rewrite that generically would think about, x plus x into x times 2 would look like this. I check whether my application node operator is addition. If not, I get out of here. Then I get the inputs. I check if they are the same. If they are the same, I return my rewrite. Otherwise, it falls back to none. And then here was a more interesting one that would be composed with that. Let's say I have sum of x and a. If a is a scalar, I can kind of pull it out and do sum of x and then multiply by a, saving this element-wise multiplication on all the entries of x. And would look not too complicated. Is the application node I returned an operator sum? If not, I get out. I get the input. Is this itself something that has an owner, meaning it's not a root variable? And if so, is it a multiplication application node? If not, I get out of here. Then I look, let's get the two variables. Here I'm already assuming like I'm being dumb, but I'm saying I'm going to check if the scalar factor is the right input. And the other I'm going to call it input. I get so basically two nodes to multiplication. I check, is the factor variable, so the right variable of the multiplication, a scalar? If not, I get out. In a more clever rewrite, I would have checked, okay, maybe the first one is the scalar and the logic still applies, but here it doesn't. If we got all the way here, we can do our rewrite. So I call the sum. So my application node was that I confirm is a sum. I call it to create a new apply node just with the first input to the multiplication itself, without the second one there. The reason I use this op is that this already has the information about what axis I'm doing, so I don't have to recreate the sum operator with the same axis. I can just reapply the operator. Once I get this new sum, I can multiply by the factor, and this is what I want to replace my original graph with. And then there will be some logic here that combines both these two rewrites and the cloning and the compute clients. You'll see later, but I'll just show you the input and output. So if you had sum add xx, we say let's rewrite with the add to mul that we defined above and see how it looks like afterwards. It looks like the 2 times x we saw. But now that we have a second rewrite, we can maybe compose the two together and try to apply both in order. And you'll see that in this case, we're able to both get the mul by 2. And once we have the mul by 2, it fit the rule of our second rewrite of lifting the multiplication out of the sum. So we sum x, and then we multiply by 2, which in this case, you might already believe it's more efficient than the original graph we had. And we just confirm we get the same output. Okay. I know this is very fast. We're always more ambitious about how much we can present than we want, but that's why we had these notebooks in the repo. You can look at them at your own pacing. I would say if you understand this notebook, and if you understand what Jesse told you, you understand like 95% of what PyTensor does, honestly. It's not more than this. Everything else is just elaboration on these simple building blocks. And the magic of, composing rewrites that think very logically about themselves and letting those kind of pile up and create nice stuff. And then eval is just, it's the boring part at the end, In the end, I want to do numerical computations. There are many ways. This is a dumb one, but, clever one might try to compile C code for the individual operators, or might, try to transpile this into Numba. And obviously, that's what PyTensor does at some point. I think it's too advanced for the workshop, but it's something that you might want to think about. How does PyTensor do those steps?
I will say, though, that everything you get in the workshop is all you need to know how to do that transpilation stuff. So if you're specifically interested in like extending to different backends, as long as you have the right mental model about like what's an op, what's an apply, right? What's a node, what's an input. Like if you kind of know this vocabulary and have the mental model of how all these things hang together, then writing dispatches into other computational backends is just trivial. Well, in principle, right? Then you get into the nitty-gritty.
Yes, and hopefully also convince yourself that writing rewrites is probably not too hard, and even implementing your new operators is not too hard. And with that, feel free to ask any questions, but the segue here is now to the applied part of the workshop. That we defined some notebooks, some exercise notebooks. I'll just mention what this. I think we have 3 notebooks you can choose for, what they are about. And the idea would be we break you guys in small groups, maybe 2 or 3, and you just hack a bit on it. And maybe won't have time to show the results, but after the workshop, you guys can just ask questions about it on the chat anytime. And it's really, I think, if you are serious about this, you'll need to actually try to write some PyTensor code, and these exercises are really just to ease it in, and we try to make them as fun as we could. So, with that said, GitHub, PyMC devs, PyTensor-workshop. And if you go to the issues, there's a pinned issue that has the outline of the workshop, and has a link directly to the notebooks of the exercises you can choose to do. And the exercise is basically one that goes over like, how do I go about implementing a new operator? One that's a bit more esoteric. How do I go about implementing new types of variables, right? We work with tensor types, which represent symbolically NumPy arrays. But you can do, PyTensor is actually agnostic to the type of variables you are operating on. So to illustrate that, we do an exercise on a new type that doesn't really exist in PyTensor, but could be added if there's a use for that, which would be a tuple type. How do I define tuples? How do I make basic operations and graphic rewrites on tuples? And then if you're more interested in really using PyTensor as an end user, not really developing or contributing to it, or like debugging code you saw, we have a simple like application of PyTensor to do the page rank algorithm, the one that historically and famously Google uses to rank web pages when you search, before they decided to just let LLM answer you what they think is best. And that's just kind of a bit like the logistic regression. Jesse just skimmed over a simple 5-6 line functions to solve a page rank exercise, and we try to build complexity gradually. So to do this, and if you guys are in it, I just need you to very quickly type on the chat what of these exercises 1, 2, 3 you would be interested in, so we can break you guys into the same rooms. Okay. Once you click in this link, you're going to go to a notebook. In the notebook, you can click in Open in Collab, and you should have a notebook that you are able to execute. Just make sure to run this first cap yourself, and you'll have the exercise. All the exercises have a test function. Once you kind of implemented what that test function needs, you should uncomment me and try to run, and it's going to give you that GIF that tells you whether you succeeded or failed. So very like immediate feedback, hopefully. Yeah. So I need you guys to type 1, 2, 3 in the chat to say which exercise you'd like to do. If you don't want to, that's fine. Obviously, this is not school. Okay, willing to. And I'm going to try to break you guys into the rooms. I don't know if I can see the chat at the same time. Professor Ricardo, yes. And we'll come in. Set the breakout rooms. Okay, so let's see. If we just have 3 rooms to begin with, and I can put people in. Okay. Jesse, can you tell me the names of people and I put them in the rooms?
Yeah, Will goes to 2, Colt goes to 1, Jake goes to 1.
Can I just take out every one of the other rooms? Okay, let me do it this
Can you
way.
just open the rooms and people can go to them? Is there...
Can they? If that works, that's better. Yeah, if we can try that. So I'll make breakout room. So there's breakout 1, breakout 2, breakout 3. And those correspond to the notebooks. Yes. Maybe. Let's see. Okay. Okay. Can people join the rooms? I think Colt is in the first room. William. Okay. There's 2 people in the first room.
But can you go once like now? There's a way to see it?
For us to see where people are?
Breakout rooms.
Yeah, I can see. Can you go to rooms and see who's where? I can see them in the breakout room, but maybe I'm the only one.
Yeah, I think so.
Okay. So there's only people in the first room so far.
The remaining group might be small enough we can just pick one.
Yeah.
Give the control over to somebody who is it to us and just work through something.
Definitely.
If anyone's brave enough.
It's stupid that it shows the people who are not on the call as well. So I just...
Where are you saying? Okay. Oh, yeah, this people list?
Yeah. Okay, what did I put that? Jake 1. There should be 2 1s and 1 2 at least. And that's it, right?
Oh, is everybody still here now in a breakout room except for you and me?
So there is Colt in the breakout room 1 and no one else anywhere. Okay. Jake is not in a breakout room. Jake, can you go to a breakout room or I have to put you there?
Oh, I can click on, I have the thing on the top.
I only see breakout room 1.
You only see breakout room 1. That's stupid. Okay. Well, I think you're alone, so you can stay in the main chat.
Okay.
Yeah, I never work with these, unfortunately, so I don't. I see a lot of folks in the breakout 1, but you are there. Okay.
The complete rewrite of PyTensor didn't have coordinates brought into it immediately.
No, but you can extend it.
I know. I need some more hours.
So you were asking, how do you go to a breakout room? I don't know how you go to a breakout room. I thought that people could just see the breakout rooms. It's annoying.
It says breakout rooms in session. at like the top of my screen, but it's like nothing.
Okay, so there's a. Which one did you want to go? 1 or 2? I can send you there.
1, please.
Okay, I'm gonna try to send. Go. Okay. Anyone else? Rob, I don't know if you're here, but you show us, and Carlos.
Yeah, I think I could go to number 1 as well.
Okay. And Rob, are you here?
I'm just trying to run a few things. So let's see.
These rooms are a mess, by the way, Jesse. I see you can here.
I would rate it as a disaster. I mean, because I can join room 1 on the top. So maybe if we just have one room next time, so you have like main room, breakout room.
Yeah, that's what's happening here. Will is implementing tuples because he wants to do date types. And
sweet, that's sweet.
I guess.
Yeah. Let's do an ops because he felt like it was more like the nuts and bolts of things.
I also want to bring the chords in. That's
that'd be nice.
Problem for future me. So let's see. Types and PyTensors. Did you define this filter in the one you did?
The one I showed now. So this is actually PyTensor stuff. So the one that I did hide was the filter, but it's not too bad. The filter is just, is this PyTensor variable compatible with this type? This Python variable, sorry. This actual data compatible with myself.
Mm-hmm.
So don't worry too much about the filter. I think it's a required method. Like I couldn't initialize a type or evaluate.
I see. And what is this? So like, this is obviously a base class, a base built-in type. What does this inheritance do?
So that's a PyTensor type is this parameterized class. So this is so the tensor type is a type, and you'd have brackets, NP, and the array. This one is if you want to create a tuple.
Mm-hmm.
I'm not very familiar with this type hints magic for classes. So I don't know exactly how does it work when you put a tuple there, but it just
magically works.
I just copied it.
Okay, so the setup is that.
Yeah, I give you the tuple already. Yeah, but now you have to play with it. Jesse, did the guys in breakout 1 manage to get started?
No one was sharing when I popped in, but I just said hi.
All right.
You want to go be Professor Ricardo in there?
I'll help them see if they are started.
I'm just a TA, man. It was time to touch the keyboard, so they all ran away. There's one other breakout room. They're working on the implement an op notebook. But so if you're keen for some teamwork, you can go there or here, or just work by yourself if that's what you prefer.
Talk to me?
I was talking to Rob in the chat.
Okay.
Sorry.
So So I'm following this trace back. I always get a bit confused with the notebooks because this is obviously just notebook stuff. So this doesn't catch any of our logic. Here, this would be built-in stuff with checks against these, right?
Yes. Yeah, exactly. Because you gave it because this filter in the tuple, I think, is just checking each entry of the tuple type against the types that's expected, right?
I see. So then this filter, which then is applied, then since that's for any type, is done here. So if I do put any in here, I would get one of the raises. And one of these, whether it's a vector or the matrix raise this then.
Yeah, exactly.
Okay. Makes sense. And is so are these signatures consistent or something?
Yeah, that's like fixed boilerplate. Anytime you do a perform, it's always going to have that signature. Anytime you do a make node, it's always just going to take a list of inputs.
Okay, but it could also be unpacked like this, so positional args.
Yeah, exactly. Here, like whatever makes sense for the op, right? Like a dot op would be A and B, but here since you have a variable length tuple.
Sure. Pack arbitrary into two. Oh, okay, back it into tuple. So I got. So then the val. Where does the val come into play here?
So the eval is hiding. It's a method of the op that you're getting through class inheritance.
Mm-hmm.
So it's gonna call the perform.
Only on the op. So
It's gonna go through the graph and call the performs, and then also do this like list singleton unpacking stuff to help you out. If like here you have this output storage 0 as a tuple, but you only care about that 0th output, so it'll unpack it for you.
understood. So the perform I saw before was returning the outputs, but because this is modifying it in place, you don't have to return. So like the perform actually isn't the final thing being called.
Right. No, this is like a PyTensor detail thing. You never return anything. So like what actually gets made is like a thunk at the end of the day. So like a fully encapsulated thing that just has no inputs and no outputs, but has side effects. So you just like call this thunk and then everything gets updated in place. So that's why you have to, instead of returning an output, you just have a storage location. This is where the output goes. That's kind of a deep implementation detail. But the consequence of it is that perform never returns.
Okay. So these, as you mentioned, these are the signature for any type of op.
And I've never actually seen one use the node. Like it has to go in there. I guess someone must use it, but typically you just use the inputs and the output storage.
You said you haven't seen what of node?
I haven't seen perform that does something with the node.
So that's the apply itself.
Yeah, exactly. So I guess like if you needed to like look up and see like who are the parents, like where is this coming from, and like reason about that for some reason, you would be able to.
I really haven't seen that. I feel like
I've never seen it before. No, I've never seen that before.
it was really enlightening when Ricardo was doing the conjugate stuff. That was pretty sweet.
Did he use that? Yeah, I guess.
I don't know. I mean, I'd have to come back again to it with a different set of eyes.
Yeah.
Okay. So implement an op that selects. Okay. So it's always gonna this will always return and apply.
Exactly. Yeah.
Right. So you'll have to get the type. So if I return since this is what is this have an expectation of a type then?
Yeah, that's going to be, I guess, the tuple type. So like this is the inputs, the input to the select tuple. So you'll pass in
it would be this tuple type.
Yeah, exactly.
And where did that comes? That comes from a filter, or no?
No, that'll be given by the user. So when you actually like you'll make this op. If you look at the test, when it says y again there, so you make a select op class with 1 in the constructor, so it's going to select on index 1, and then you pass in a tuple type.
So I should be able to kind of assume this type of structure.
Yeah, exactly. I think.
And then
I didn't do this one yet. Yep.
So like if I do this as opposed to, I think here there was a maybe there wasn't. Let me see. So this would be output, right?
Mm-hmm.
Maybe something like that. So let's say that gets the type.
Mm-hmm.
Selects the entry. Well, I don't want the type. I want to have that specifically, I think.
That's a good question. I think you want the type. I thought type was right, but I haven't done this one before. So let's just try it and go with your gut and see what happens.
Okay. Let's see. So then what would actually be happening here?
So now you're in Python. So you just have to reason about like what are the actual inputs and what are you actually doing.
And then so the inputs would be these tuple again, right?
Yep. And it's always a list. So you have to like if it's 1, you gotta unpack it.
Yeah. Okay. So then, what's the role of the output storage? So that why was this being done again?
Yeah, so it's like a buffer where we're going to stick the result of the computation, and it has to be a list of lists with one list per output. So if you had like 3 outputs, you would say like output storage. You would actually change the second 0. I always do it both. I apologize. I always mess it up. I think it would be output storage 0.1, output storage 0.2, output storage 0.3. Let me look real quick.
So let me see. I don't think this is right because these are the types getting put in as opposed to the data is.
Because when you're inside perform, you'll have data always.
Okay, so the inputs then actually is the data.
Yeah, exactly. That'll be the incoming tuple. And you were right. You changed the first number, so it would be 1 0 0 and then 1 0 if you had 2 returns, for example. I think this is all right. You just have to grab the correct object out of value, right?
Yeah, but then so what type is this then? This is value is then tuple type?
Yep. No. This is an actual Python tuple.
Ah, I see.
Yeah. Yeah, perform is Python land and make node is symbol land.
Okay, well, let's try. Let's use the feedback loop that's here.
Entry types. So why is tuple a variable?
Let's see. So let's look at the test, and we will make the test work as opposed to the general logic. So pack tuple. This was the tuple type. Tuple type, and then
the make node.
so this is just the indexed. And then this. What were you saying?
I was thinking about, so what if make node is always, so make node the out, it's saying the output, or sorry, the tuple is a variable. It's not a tuple type. Which is, I guess, fine. Because a tuple type is a variable, right?
Yeah.
If you go back to the beginning, does it have any special no, it's not a variable. It's a type tuple. What if we do something really dumb? What if we just say like the output is just tuple.type and we return it just to see what happens.
Tuple.
No.
Inputs of that apply.
Oh yeah, this is just a like a idiosyncrasy of PyTensor, that the inputs and the outputs always have to be lists.
Okay. Inputs and outputs, you said.
Yeah, everything.
The outputs argument to apply must be a variable. No owner. So let's see. So this has an owner.
So there you have a type error there, right? You got the type of the variable, but you need to create a new variable with that type.
Okay. So then the tuple type. So
Or well, you have to create a variable with the right type. Sorry. So tuple type, I guess, is a well. Check what tuple type is. That's the easiest. You just print that.
so I was confused here where
So it's the difference. You're confused about the difference between variables and the types of the variables.
yeah, so this right here is coming through as a variable. So
So that's a variable whose type should be a tuple type. You could put a check there. You know, this operation only makes sense if that type is a tuple type. Yeah. Now, having that, so that's kind of validation of the input. Now you make notice kind of figuring out, if I have this operation with this type, what should be the type of my output?
So the type is going to be the entries, types, self-index. Then each one of those is a type.
I think they're already a type. I don't think you need the dot type.
Oh, they're already types. Yeah, correct.
But that's the type. But you need to make a variable of that type. What you got, what I would call that expression is the output type. I wouldn't call that output.
And then, so
you can
be initial. All types can be
exactly.
initialized like that.
Yep.
That's it. Yeah. Otherwise, you would have to. Okay, and now check what happened. Is instance tuple type? Yeah, you made an error there also.
This is
the variable is just a variable. What you meant to say is the type of the TPL variable is a tuple type.
Okay.
You can keep the assert, just add a dot type to TPL. So like TPL is a variable, but then it has a type which can be many different things.
No, it's just a small typo, I guess. I don't know what that was called.
Okay, so this is getting passed, and then that would mean that this variable needs to be done here.
Yeah.
Mm-hmm.
It's a bit confusing, this distinction between the two, but it's important. Like everything is a variable and that doesn't tell you anything about it. What matters is the type of that variable. It's the same thing that like everything in between variables is an apply, but that doesn't tell you anything about it. What you care about is what's the operator of that operation of that apply.
Mm-hmm.
I got on this with disconnected type. I was checking for disconnected gradients, but I wasn't checking for the dot type of them.
Yeah.
Okay, that makes it takes it.
If you want to go help the guys, Jesse, I was already being a tough teacher there.
So okay, I'll jump over.
All right, so We'll also have the. It's always going to be a vector and a matrix. And then what was the
You have there the vector and matrix.
Yeah, I'll just copy it. Okay, so then having it separated here might be beneficial because then I can just so these are the types.
You have no variables so far, only types.
Types, yeah, correct. So then
So now the idea is, so this is a function that expects a tuple with a vector and a matrix as inputs. You actually don't pass. So you actually don't pass the vector and the matrix. You pass already this tuple with the two things.
sure.
Right.
So let
So
me
that would be,
this the tuple,
yeah.
and then the inputs then is. Do I call it with first and second?
No, you don't need you don't need to call anything. That just defines a root variable. The type is already, you already have all the information because it already tells it's a vector and matrix, right? No. You literally just write tuple. Imp equals tuple and call it to create a variable with that type. Yeah. And now what you're getting confused is, and this is chaining on the previous exercise, right? Where you wrote an operator that can unpack a tuple. And that's what you need to do here, yeah. To then work with whatever the vector and matrices of this tuple are.
So the first is then the, what is it called? What was it even called? The first one. But do I have to call this this right here?
Yeah, so the reason about like the first line is initializing a op with a given parameterization, right? But it's not yet telling you inputs and outputs. That's what the second step is.
Okay, so I would pass this input.
Yeah.
And then I can pass the same input.
Yeah.
And
you can do a first .dprint to see if it's looking like what you'd expect. Yeah, and you can also, the dprint accepts an argument, print type. If you do print type equals true, it's also going to tell you.
True,
Sorry.
true. Like
No, the true, false. My bad. False is the default. If you do true, it's going to show you what are the types of the variables. So see, you have the tuple, that's a vector matrix, and select index 0 gives you a vector, right? And this is an actual vector you can work with.
Okay. Well, my single test pass, I'm assuming that it is doing what I want.
Yeah.
Okay, that seems like it checks out then.
Mhm.
And what is that? What is it called? Pack them into a tuple in the reverse order. So so these tuple, the types, is it kosher to reuse them? Is it like if I go here, do I have to redefine?
But you don't, right? So you only need to, so as a user, now you are a user, right? You are working outside of implementation. You only specify types for the root variables, right? Everything else is the application of operations, and the operations know how to create intermediate types, right? So the output tuple itself is going to be an output of some operation.
Okay, but I don't have an
You have
op
that.
to
You
cap
have.
them together, do I?
Yeah, I gave you
Okay.
that. Yeah.
Let's see. Okay.
And maybe now if you check the, or whenever, the make node of pack tuple, it will be a bit more obvious what's going on with that boy.
And here I'm going to do the second and the first, so that's the reverse order.
Mm-hmm. Yeah, exactly.
Okay, so this is really just even the out.
Yeah.
Because that's going to be a variable, right? Sweet. Thanks for that. Those tips. So you think implementing datetime would be tough?
Well, the issue with datetime, so in PyTensor is easy. The question is what you want it to do in the different backends. Like for instance, JAX doesn't have anything related to date types, right? So you couldn't compile these to a JAX backend.
Sure.
JAX would be happy with tuples, right? JAX has tuples natively. So that's a bit the case with DIMs also, right? We could implement DIMs just fine. They can even work directly with X-array objects in the PyTensor default backend, but then neither Numba nor JAX would know how to work with X-array objects, right? So that's not so much about implementing types, but I guess it's kind of a layer of indirection of converting, datetime code or converting kind of X-array or DIM-based code into, in the end, just vanilla NumPy code that can compile directly to these backends.
Yeah. Well, so I never had in my mind that it would use X-array actually.
Yeah, but like the datetime, you were thinking about literally NumPy arrays with date, right?
Yeah, I mean for that they would.
Yeah, so I guess Numba might support them. I never saw. I don't know. I don't think JAX has datetime variable types, but yeah.
So let's see what's going on here.
Yeah, so look at the graph. Look at the graph you're going to be playing with, which is the one that's deep printed.
Right? The one here, yeah.
Yeah, so the point is the rewrite didn't do anything, but if you look at that graph, it's obvious for you that it should be simplified a lot, if you think about it, right? It's packing X and 1, then it's unpacking and taking the first entry, X, and it's subtracting that from X itself. So the pack tuple and select tuple are just in the way of basically finding this is an x minus x operation.
Yeah, so this is really just trying to get here. What's x again? X.
Is literally selecting the first
be
entry
like
of
zero
the
or something.
tuple that has x there. Yeah. I called it x again to emphasize the meaning. I could have called it y, right?
And so
the point is when because we added tuples to it, like PyTensor doesn't know anything about tuples. It could do, the previous was saying it can do constant folding. If all the inputs are constant, it can just compute the outputs, that's fine. But that's the only thing it can do right now. So now we are teaching it like, if you pack a tuple and then you unpack it with a select, basically I can just skip that step and get the thing you put in the first place.
yeah. Okay, so then so the F graph, what's the object here? That's
Yeah, F graph you can ignore for this purpose. It's just passed, but it's something that contains like global information about your graph. But you should be able to reason just about the node. Yeah.
Okay, so then here I'll have the hop, right? So I need to, I guess, would you typically have a rewrite for the case where it's a sub into a select and then a select into the sub?
No, so the nice thing is probably PyTensor already has a rewrite of sub x, right? So that you don't need to do. So you should think about just the new stuff you added. So the thing you want to think about is select on a pack, right?
Okay.
Yeah.
So then I need to detect, so if it's not, how do I get the a node hop?
Yeah.
And it's like, can you do this?
Yeah, that's valid.
So that's the short circuiting, right?
Yeah.
Okay, so then
So now you know that if you're here, you have a select tuple node. Yeah. So the next step is checking.
About that again.
Yeah.
That's the one we were. Okay, so then.
You already passed it.
Yeah. Okay. So then I'll have all the entry types.
So you don't.
No, that's not a tuple.
Yeah,
that's for a tuple. What's the
Yeah.
I would need to look into the inputs or something.
Yeah, exactly right. Just like you matched the first part of the pattern that you need to match. Now you need to check.
Okay.
You could be a tuple, select tuple of something else, right? It doesn't need to be pack tuple.
So I know that this is going to be a single.
It's going to be a tuple, yeah, or variable, whatever you want to call it, yeah.
But
no, it's a single one.
Okay. So then I need to do input what's it called again? Pack tuple. So I'm trying to do shortcuts. So this right here would be the inputs, right?
Yeah, but it would be multiple, so that should have a star argument there in the doc strings. So there could be several inputs to the make node.
Okay. So this would be the list, but this is like a list itself.
Yeah, or yeah, that's a list. Check the make node of pack tuple to give you more intuition of what pack tuple, like how it looks like in and out, because that was provided by me, right?
So in this rewrite, I then do a similar thing to make node. I return and apply.
No, the rewrite, you return a variable that replaces a variable for every output of the node that you are replacing. So your select node returns a single variable, like, right? You return a variable that replaces the output of this node, not an apply. The reason is maybe you have a node that you return that has multiple outputs, and you replace them by variables that come from different nodes. So it does need to be a single node, like a single node that does the replacement. And you see the type hints here are saying that, right? You return a list of variables or none. The input to that node input is an apply. So it's different. The input and output are a bit different in this regard.
Sure. So then I think, can I not just do the, and then this is the, so then the select dot index.
Okay. And that has to be a list. The rule is you have to return a list. Okay. And you can run it. You're gonna see a failure. You just miss something in the, about like how do you go from things to things. But the logic, the fundamental logic is sound.
So variable doesn't have op. So
so input is a variable, right? Not an operator. Yeah. And there's that thing. The variable comes out of a application node, that blue box. That's the thing that has an operator. And you get it by the imp.owner thing.
Okay, to repeat that. So I'm not looking for the.
You're looking. So imp is a variable. Like you're looking for the operator that defines this variable, right? And there's a bit of indirection here. You need to get to the application node, this apply that you get doing imp.owner. Oh. Yeah, that's it. Okay, but then you still have an error below. Imp inputs is also not a thing. Wouldn't make sense a variable to have inputs itself, right? It's the application of, it's the owner.inputs basically again, right? Is this a bipartite thing? There's always something in between two variables. Okay, and you're almost at the end now.
Sure.
Then select is a node, and then the thing,
Is it inputs?
No, that's fine. Tuple, what you called tuple is already the inputs. Maybe I would have called that tuple inputs, but that's okay. Yeah, that's the thing you want to index on. But the indexing thing, select, does not have an index. Select is not the object you think it is. Yeah, select is the node.
Sure.
That has the operator. Yeah. No, it's already the node. It's a bit tricky. That's the thing the function gave you. That was passed to you to this function. Not a type either. Op. Yeah.
There's three choices.
It is. So but that's the thing, like the application has inputs, outputs, and an op. And now I guess you're okay. What was the problem? What did you complain about now?
Is that the input?
Okay, so this is not an issue in your, it's the test is doing more. You did an assumption there, an implicit assumption that input owner always has an op. Actually, you made an assumption that imp owner always exists. But if it's a root variable, it has no owner. Owner is none. I guess we were testing that specifically. Yeah. And now it found out that this graph is equivalent to 0.
So X scan out there. Alrighty. Oh, so this is the last one?
Yeah.
Interesting. Cool, let me try to do this one. So make a new select opt.
Do you get the difference?
So here I have a tensor.
Yeah, scalar 6 in 64. Yeah. So the point is the indexing now is not like static. You don't always know it's going to be 0, 1, or 2. It's going to be something that can change at runtime. So it's itself symbolic, the indexing operation, right? So the user might say, I want to, in this function call, I want index 0. The next, I want index 1. You don't know that yet.
Okay. And then would the perform be similar?
Yeah, the perform is similar.
So let me see what I had here. So it's again this type, so I can do that.
Now you get value and index. That's the point. Now index is a runtime variable. Here.
Okay, so that would be corresponding with these.
Yeah, that's usually the case.
Okay. And then so this depends on then the backend.
That's fine. So now you have Python objects here, right?
Yeah, but
so you can just
so like I mean depends on what like I know you probably can just do this.
yeah.
And then I'm guessing that. So this would be.
So it was promised it would be basically a NumPy 0 size in 64 array.
Sure.
Which you can index with. It could also be directly an int type, but just not to introduce a new import, I went with a 0 sized array.
And then this is going to be a vector, so this should technically work.
Yeah, there's going to be a tuple, yeah, and you can use it to index.
Okay. So this would also, for my reassurance, maybe to give me. What does that come out to be?
Tensor type, PT tensor type, if you want. Yeah. And you could check more things, like you could check the shape is 0, the D type is int, if you wanted, right?
So if I wanted to, so this here, like when someone does define this, say here, there, I'm working with this and I'm doing something similar to here. So is this right here? Is that just me doing the symbolic that?
Yeah.
And then you call it again to get this.
Yeah, to get the. Well, I want you to pass me the class I create the op itself.
Okay.
Yeah.
Would
Yeah.
Let me try to do this. But the asserts are not required. That would just be for user robustness.
Yeah. Just
and that happens at initialization. That's what I was trying to get. Is it at initialization or
these checks? No. So these checks, the make node happens when you ask make me an apply node for a given input. So it's when you call the op, the thing you created above with some input. So that happens in the select op when I call there with XX and index.
Gotcha.
Yeah, that's when that call is going to call make node and retrieve the first output and pass that back to the user.
Okay. Where was I? Shows so if this is going to be that doesn't seem like it would work.
Yeah.
I need to get to the
So that's what I'm asking there with what constraints. Like you cannot do this you cannot do this operator like generically.
Understood.
There's
so
only
then,
some cases where it's going to be valid, right?
it's like the actual the scalar value. This is where I'd have that constraint of, and then so I would have to get the value somehow, right?
Okay, so there's two ways you could do this. There's one way where you constrain index to be a constant, right? That's the only way you can get the value of it. But that again, then that's not really gonna do what you wanted to do, which is to allow the index to change over time. And the test is not gonna pass you a constant index.
Okay. So I can't.
So if the index, if you're not allowed to know what the index is, you have to reason what kind of operation is this still valid even if I don't know what the index is.
So I do have this assumption that it's a scalar. Was that said?
That's fine. That's given to you. The thing is, like, you have a tuple that can have arbitrary stuff in it, and I'm going to index, but I'm not going to tell you what the index is. And you have to tell me what's going to be the output type of this operation. You can put constraints on the input, but one of the constraints cannot be that I tell you what the index is. That's off the table. I'm going to call the function with the index being two different things at two different times. There's still a way in which you can tell me, you can say, okay, this is going to be valid, provided that something about the tuple type.
Like something with the length?
You don't need to know the length? That doesn't, okay, yeah, that's on me. I'm going to give an index with the right length. That's on me. Okay. So the constraint is like, basically you need to know what's the output type, right? I'm giving you very little. I tell you what's the input type of the tuple. You know that, okay?
Yeah.
So the trivial case is you can do this operation if all the types are the same in the input tuple. Because then it doesn't matter what I select, I know what's going to be the output type.
Sure.
So that's the constraint you need to be able to do a symbolic indexing on the tuple.
So it wouldn't be possible to do elsewhere. So I'd have to do assert all. I maybe have to do it still. Something like that?
Yeah, something like that. I'm not sure the set is going to work. I think so, but we'll see that.
Okay.
Okay. Once you know these, now you can tell me. Now you don't care about what my index is, right?
Sure. Understood. So the make node is just trying to find the type.
Yeah, so the PyTensor is basically a strongly typed kind of version of Python in a sense.
Mm-hmm.
I don't need values, but I need exactly to know what the types of the things are coming in and coming out. Okay. Check what. Okay. There was a rule about what should happen if that's not if you cannot enforce. I think you have to raise a type error or something. I don't remember exactly.
Possible.
I think it. Yeah. No, I did it. Type error. Check what the test is checking gets raised. I think your set logic is not correct, right? It's not that they have to be the same exact object, they have to be the same type. So I think you have to use a...
Yeah, makes sense.
You have to, like the loop.
Where did I go too far? Yeah. So the entry types, these are all types.
So these are instances of the class, of a class type, right? But they need not be the same object.
Type.
I also don't think that works in Python stuff. I think you really have to do like grab the first and check all the remaining ones are the same type or something like that. I don't know if types are hashable by default.
Yeah, they're probably not.
No way.
So I do have this.
Yeah. So you can go to the next, and then you can check if the type is the same. Which I think is different. Like equality does not require they are hashable or something.
So these would be Python types.
Yeah. Well, they are not. No, they are not yet Python types. They are classes. They are classes of the PyTensor type thing, which is a bit confusing.
Can I do equality on this?
You might be. Let's see.
Yes. Sweet.
Yeah, so that was it.
Nice. Cool. Well, thanks, Ricardo.
Hope you learned some things.
Definitely did. It's definitely different doing it.